For the last decade, Western legacy automakers comforted themselves with a very specific, arrogant assumption. Chinese engineers could dominate pure electric vehicles because batteries are mechanically simple, but they would never master the brutal, microscopic thermodynamics of a world-class internal combustion engine. The established automotive cartels in Detroit, Stuttgart, and Tokyo universally treated their highly complex multi-gear transmissions and turbocharged powertrains as an unassailable engineering fortress. The standard consensus across the global auto market held that while a new market entrant could easily slap a lithium pack onto an axle, it took a century of institutional memory to orchestrate a vehicle that seamlessly blends gasoline and electricity at high highway speeds. But hidden inside the advanced propulsion laboratories of Chery Automobile, a team of powertrain engineers just completely shattered that comforting paradigm. They did not settle for building a simple commuter car or copying a basic Western hybrid design. Instead, they developed the Kunpeng dedicated hybrid transmission architecture, anchored by an impossibly complex 3-speed mechanical matrix. When this hybrid system is dropped into a mid-sized 7-seat sport utility vehicle like the Tiggo 8, it operates with a level of thermodynamic efficiency that defies standard industry expectations. It does not simply use an electric motor to assist a weak gasoline engine. It utilizes a dual motor arrangement coupled to 3 distinct physical gear ratios, allowing both power sources to shift gears independently. This breakthrough completely detaches the plug-in hybrid vehicle from the historical efficiency traps of traditional engineering, launching an aggressive cost-to-performance assault directly into the heart of the global automotive sector. If a single manufacturer can mass-produce a complex, multi-gear hybrid powertrain that achieves elite fuel economy without demanding a premium European price tag, the legacy automotive business model fundamentally breaks down. The decades-long technological moat, once protected by Western internal combustion patents, is quietly evaporating. The Western monopoly on high-end mechanical engineering is officially over, and the machine that dismantled it is currently rolling onto global shipping docks. Consider the silent, deeply frustrating mechanical failure currently suffocating the modern plug-in hybrid vehicle market. For the average consumer looking to transition away from pure fossil fuels, the modern plug-in hybrid promised the ultimate compromise: electric commuting around town and long-distance freedom on the highway. But under the hood of almost every legacy European and American hybrid SUV, this promise hides a devastating engineering shortcut known as the dead battery penalty. To meet strict government fleet emission standards as quickly as possible, Western automakers rush these vehicles to market by lazily bolting a heavy electric motor and a lithium battery pack onto their existing traditional gasoline powertrains. In short, low-speed city traffic, the system performs adequately, but the exact moment you transition onto a high-speed highway and the battery drains, the vehicle undergoes a catastrophic performance collapse. The driver is suddenly left dragging up to 400 pounds of dead battery weight using an overworked, highly inefficient, small-displacement gasoline engine. The vehicle's fuel economy drops off a cliff, the transmission hunts frantically for gears, and the entire driving experience degrades into a loud, vibrating struggle. The macroeconomic consequence of this engineering shortcut is severe, as drivers across the globe are forced to pay exorbitant premiums for vehicles that operate efficiently only half the time, effectively trapping them in a cycle of high fuel costs and mechanical disappointment. If you are into stories about technology changing the world in ways nobody expected, hit that like button and subscribe. Now, imagine an industrial paradigm where the physical and financial penalties of hybrid weight management are permanently erased from the consumer spreadsheet. When an automaker replaces a lazy bolt-on hybrid system with a bespoke, multi-gear, dedicated transmission, the entire behavior of the vehicle shifts from a compromised patchwork to a highly optimized thermodynamic engine. A family embarking on a 1,000-mile road trip across varying terrain no longer needs to worry about their battery running flat or their fuel consumption doubling on the highway. The vehicle's internal computer manages its own energy split with surgical precision, operating with the relentless efficiency of a localized power grid. If the SUV faces a steep mountain incline at highway speeds, the multi-gear transmission alters the mechanical leverage for both the gasoline engine and the electric motor simultaneously, maintaining peak power without burning excessive fuel. In real terms, this completely resets the financial and expectations trajectory of the mass market consumer. The family SUV stops being an expensive, compromised compliance tool built to satisfy government regulators, transforming instead into an instantly scalable asset that beats traditional gasoline cars on the open road. For legacy automotive corporations holding monopolies on premium, highly complex drivetrains, the implications of this mechanical shift are absolutely devastating. These multi-billion-dollar conglomerates that have spent generations controlling the market through brand prestige are suddenly finding themselves mechanically outclassed. Today, the race to build the next generation of global automotive dominance is no longer about who possesses the most historic badge. It is a quiet struggle to master the intense mechanical tolerances of multi-gear hybrid integration. To understand why this specific transmission architecture is causing sheer panic inside European boardrooms, we have to trace the historical arrogance of the Western hybrid strategy. For over a century, legacy automakers treated the internal combustion engine as their undisputed sovereign territory. When stringent new emissions regulations swept across the globe in the late 2000s, these massive conglomerates were caught completely off guard. Instead of initiating a painful multi-billion-dollar redesign of their entire powertrain lineups from the ground up, European and American engineering divisions collectively agreed on a massive industrial shortcut. They assumed they could simply appease regulators by retrofitting their existing, highly profitable gasoline vehicles with basic electrical assistance. This defensive posture created a multi-layered mechanical failure that would ultimately leave the door wide open for Chinese engineers to invade their most profitable markets. The first distinct phase of this failure stack was the introduction of the bolt-on hybrid architecture. Western manufacturers took their massive, heavy, traditional 8-speed automatic transmissions and simply sandwiched a single undersized electric motor between the engine block and the gearbox. They did not integrate the systems, they merely bolted them together to pass low-speed emissions tests. In stop-and-go city traffic, this crude arrangement functioned adequately enough to secure government subsidies. But mechanically, it was the equivalent of strapping a small outboard motor onto a massive diesel yacht and expecting it to win a regatta. The two power sources were constantly fighting each other, relying on outdated fluid-torqued converters that bled raw kinetic energy away as ambient heat before it ever reaches the wheels. The second phase of the crisis manifested as the severe physical weight trap. Because these legacy automakers refused to fundamentally alter their legacy chassis platforms, their new plug-in hybrids were forced to carry the worst elements of both worlds. The vehicles housed a massive, heavy iron combustion engine, an incredibly heavy traditional transmission, and hundreds of pounds of lithium battery packs all simultaneously. Think about what that means. A mid-sized family SUV that previously weighed a manageable 2 tons suddenly ballooned into a sluggish, overweight behemoth. The suspension struggled, the tire wear accelerated violently, and the entire vehicle required immense amounts of raw energy just to overcome its own rolling resistance on the asphalt. The third and most definitive phase of the collapse was the catastrophic highway failure, universally known in the industry as the dead battery penalty. The fatal flaw of the bolt-on hybrid is that the small electric motor is entirely responsible for masking the extreme weight of the vehicle. The exact second that small battery pack depletes on a long highway road trip, the electric motor shuts down and becomes dead, parasitic weight. The undersized gasoline engine is suddenly forced to drag the entire bloated vehicle up to speed entirely on its own. The fuel economy completely shatters, often dropping below the efficiency of a standard, decades-old gasoline car. The transmission hunts violently for gears, the engine screams at high RPMs, and the consumer is left paying premium luxury prices for a fundamentally broken driving experience. Traditional hybrid deployment models had hit an absolute thermodynamic dead end. The legacy sector was trapped in an exhausting cycle of adding more weight to solve problems caused by weight. But here's the thing. The breakthrough that finally solved the highway penalty did not emerge from Stuttgart or Detroit. it emerged from Chery automobile, where engineers abandoned the flawed concept of the bolt-on motor completely. They realized that the only way to achieve peak mechanical efficiency was to rip out the traditional gearbox entirely and build a unified multi-speed transmission where both the engine and the electric motors could physically shift gears simultaneously, setting the stage for the most complex automotive drivetrain ever mass-produced. At the absolute center of this mechanical disruption lies a radical reimagining of the internal combustion engine itself, pushing traditional gasoline physics to their absolute structural limits. While legacy Western automakers treat the gasoline engine as a finished static technology that simply needs a larger battery to offset its emissions, Chery's thermal division engineered a bespoke 1.5-liter turbocharged engine, designated the 1.5 TGDI, specifically optimized for hybrid duty cycles. The core breakthrough is the implementation of a highly aggressive Miller cycle combustion process, paired with an ultra-high compression ratio. By delaying the closing of the intake valves during the compression stroke, the engine allows the expanding gases to do more physical work against the piston head, effectively extracting more mechanical energy out of every single micro drop of vaporized fuel. This thermodynamic configuration pushes the engine to a verified peak thermal efficiency of 44.5%. A figure that sits at the absolute upper boundary of what is physically possible for an internal combustion engine. In plain English, this means that the gasoline engine under the hood is not an afterthought or a weak generator. It is one of the most efficient thermal engines ever mass-produced, extracting nearly double the useful energy from a gallon of gasoline compared to a standard car engine from a decade ago, ensuring that not a single watt of chemical potential is wasted as ambient exhaust heat. To sustain this ultra-high thermal efficiency under severe workloads, the cylinder heads are cast from a proprietary high-conductivity alloy capable of withstanding massive peak firing pressures. The fuel injection system operates at a staggering 350 bar of pressure, atomizing the gasoline into a microscopic mist that burns with absolute geometric uniformity across the combustion chamber. This extreme level of atomization prevents the formation of localized hotspots within the cylinder, allowing the engine to run lean without risking catastrophic pre-ignition or engine knock. The mechanical friction inside the block is systematically minimized through the application of low-friction diamond-like carbon coatings on the piston rings and valve trains, ensuring that the engine does not consume its own power, just keeping its internal components moving. In real terms, the mechanical precision required to maintain this level of combustion stability under high pressure is immense. If a human engineer sat down and manually calculated the fluid dynamics of that fuel spray across a single second of engine operation, it would take them lifetimes of labor just to map the turbulence of a single stroke. The true mechanical masterpiece that bridges this ultra-efficient engine with electric propulsion is the dual-motor, 3-speed dedicated hybrid transmission. The legacy automotive industry has long relied on single-speed electronic, continuously variable transmissions, which operate smoothly in urban environments, but suffer from high mechanical drag and severe efficiency drops when forced to run at sustained highway speeds. Chery shattered this constraint by engineering a compact 3-speed transmission housing 3 independent wet clutches and a highly complex planetary gear train. This mechanical configuration allows both the 1.5-liter turbocharged engine and the dual electric motors to independently shift through 3 distinct physical gear ratios. By offering 3 separate mechanical steps, the transmission can orchestrate 11 distinct combined speed ratios, allowing the vehicle's internal computer to continuously alter the mechanical leverage between the power sources and the asphalt. Think about what that means for a sovereign wallet and the global supply chain of automotive components. By allowing the electric motors to shift gears alongside the gasoline engine, the transmission acts as an immense physical force multiplier, maintaining a staggering 98.5% mechanical transmission efficiency across all driving conditions. Because the dual electric motors can utilize multiple gear ratios, they do not suffer from the high RPM efficiency drop-off that plagues standard single-speed electric vehicles on the open road. At low speeds, the transmission runs the motors in a parallel configuration to deliver massive torque. At highway speeds, it seamlessly shifts to a higher gear ratio, dropping the electric motor RPMs into their absolute optimal sweet spot. The mechanical packaging required to fit 2 powerful electric motors, 3 clutches, and a 3-speed gearbox into a casing no larger than a standard carry-on suitcase is a masterclass in modern metallurgy and computer-aided design. The gears are sliced with microscopic precision to minimize gear whine and backlash, ensuring that the continuous coupling and decoupling of power happens with total mechanical transparency. In real terms, this tight mechanical integration delivers an unexpected economic equalizer. The most capable, highly complex mass-market hybrid drivetrain now costs less than a 5-year-old Honda Civic's replacement transmission assembly from a European luxury dealership. Orchestrating 545 Newton-meters of combined torque within a tightly packed engine bay generates an immense, potentially destructive thermal payload that would instantly melt a standard automotive cooling system. To prevent catastrophic thermal runaway when the dual electric motors and the turbocharged engine are running at maximum capacity, Chery's engineers developed an advanced dual-circuit, double-sided intelligent water cooling network. The system separates the high-temperature cooling loop required for the combustion engine block from the low-temperature loop dedicated to the sensitive power electronics and electric motor windings. The inverter, which acts as the digital brain routing hundreds of amps of current between the battery and the motors, is sandwiched between custom aluminum cooling plates that continuously pull heat away via a high-flow electronic water pump. In plain English, the vehicle houses 2 completely separate radiator networks working in perfect harmony. One keeps the roaring gasoline engine at its optimal operating temperature, while the other prevents the high-voltage electrical components from overheating, ensuring total system reliability even when towing heavy loads up steep mountain passes in midday heat. The integration of the 19.27 kilowatt-hour lithium iron phosphate battery pack into the vehicle's structural subframe represents another massive engineering hurdle. Instead of simply dropping the battery into the trunk floor and ruining the interior cargo space, the pack is engineered as a load-bearing structural element bolted directly underneath the passenger cabin. The battery casing is stamped from ultra-high-strength hot-formed steel, protecting the cells from severe side impacts while lowering the vehicle's overall center of gravity. This specific battery chemistry was chosen deliberately over volatile Western nickel-manganese-cobalt alternatives. The LFP matrix offers extreme thermal stability and an architectural lifespan that allows for thousands of rapid charge cycles without experiencing meaningful capacity degradation. In real terms, the physical durability of this structural pack is staggering. The armored steel enclosure protecting the lithium cells is built to withstand impact forces equivalent to the weight of 8 full-grown African elephants pressing down on a single structural node during a high-speed collision. As extraordinary as the 44.5% peak thermal efficiency, the dual-motor 3-speed dedicated hybrid transmission, and the structural load-bearing battery integration are, they are still just individual triumphs of automotive component manufacturing. When you look at the entire system, the Miller cycle adjustments, the 3 wet clutches, and the dual radiators, they appear to be separate, distinct mechanical victories. But there is a hidden structural masterstroke that seamlessly connects all of them into a singular weapon system. The true breakthrough of this collaborative vehicle architecture is not simply the automation of gear ratios or the precision of computer-controlled electrical routing. It is a profound, invisible inversion of standard engineering survival tactics that solves the most fatal constraint in the history of plug-in hybrid distribution by executing a complete deletion of resource strain from the initial vehicle footprint. Remember that in a traditional green energy automotive campaign, achieving sustained long-distance efficiency is an agonizingly slow process of battery conservation, where the first drivers to hit the highway face the highest cost of fuel infrastructure. For decades, Western nations have trapped themselves in a defensive posture, relying on oversized, heavy battery packs to push their vehicles down the road before the inevitable engine penalty kicks in. The multi-gear hybrid architecture shatters this conventional approach by doing the exact opposite. The internal computer does not merely treat the gasoline engine as a passive backup generator, to be used only when the lithium cells drain completely. It acts as an active torque partner that uses the 3 physical gears to constantly manipulate the engine's RPMs, transforming the entire powertrain into a localized dynamic kinetic balancing engine. This intentional mechanical manipulation acts as a high-stakes thermodynamic shield, essentially transforming the transmission casing into a protective energy buffer. When intense torque loads stress the system at high highway speeds, the submicron planetary gears force both the electric motors and the gasoline engine to share the physical work, preventing either power source from entering its inefficient operating zone. This structural coordination slashes the highway fuel demands of the mid-sized SUV by up to 50%, while simultaneously firing the harvested kinetic energy back into the battery pack to maintain a permanent state of charge. The engine stays quiet, the battery stays charged. The vehicle wins the highway. This is the exact puzzle piece the legacy, energy, and automotive sector missed entirely. By treating the physical vehicle as a mass-produced active generator within a digital network, rather than an irreplaceable passive consumer of external power, the entire timeline of global automotive self-sustainability is violently compressed. The project uses the raw manufacturing scale of automated printing and casting factories to achieve a permanent shift in geopolitical leverage, proving that the traditional, sprawling, rural solar farm and legacy Western hybrid strategies are now completely obsolete. If this multi-speed dedicated hybrid technology successfully scales across global commercial networks, the geopolitical balance of automotive manufacturing power will be permanently redrawn. The ability to eliminate the multi-billion-dollar burden of long-distance transmission infrastructure and heavy battery raw materials changes the fundamental mathematics of how a nation secures its transport sectors. When a sovereign state no longer has to negotiate for massive tracts of remote flat land or import vast quantities of expensive nickel and cobalt for oversized EV batteries, it can project economic power at a fraction of the traditional cost. To understand the immense scale of this shift, look at history. When the United States established undisputed industrial dominance during the middle of the 20th century, it executed a qualitative strategy that relied on an endless network of centralized fuel supply stations linked by the massive U.S. interstate highway system. Today, that specific infrastructural luxury no longer exists on a compressed economic timeline. By deploying automated, highly integrated, multi-speed drivetrains directly onto the assembly lines of its global manufacturing hubs, China is executing a raw industrial maneuver designed for an era of hyper-dense urban centralization and resource scarcity. While Western nations struggle with multi-year supply chain retrofits and labor disputes to install a single horizontal battery factory or legacy engine plant, the Chinese industrial base treats hybrid vehicle deployment like a high-throughput manufacturing chain. If an adversary must spend a decade constructing charging infrastructure and hundreds of millions of dollars building remote battery arrays to power a transport fleet, their defensive capacity becomes financially bankrupted when facing a factory floor that prints highly efficient, low-cost hybrid drivetrains every single week. Now, here is the honest concession. Today, this advanced 3-speed dedicated hybrid architecture introduces a significant structural vulnerability that engineers have yet to completely solve. Because the transmission relies on 3 separate wet clutches and a highly intricate planetary gear train, its long-term mechanical reliability under continuous heavy towing conditions drops significantly compared to the simpler, single-speed ECVT systems used by Japanese legacy manufacturers. If a consumer routinely subjects the vehicle to extreme structural loads or fails to maintain the specialized transmission fluids, the complex clutch engagement plates lose their precise calibration, causing a temporary breakdown in smooth power delivery. Yet, do not mistake early mechanical sensitivity for a reason to doubt the trajectory. When early automatic transmissions were deployed by Western automotive firms in the 1940s, they faced massive skepticism due to their high failure rates and extreme manufacturing costs. Yet they rapidly evolved into the low-cost backbones of modern global transport. The financial and physical ceilings for legacy utility and automotive companies have already been permanently breached. while Western defense budgets and infrastructure funds remain trapped in the cycle of buying low-volume, land-heavy horizontal platforms or simple compliance vehicles. The future of territorial energy security is quietly transforming into a downloaded film deployment. The ultimate transition into the next century of urban resource independence will not require a new generation of sprawling infrastructure networks. It will simply require pressing print. As Chinese automakers prove they can dominate not just the electric future, but the complex mechanical present, how long can legacy European brands survive on badge prestige alone?